Hello, everybody. The last section in the semester is not technically from any particular lesson in the course. There actually are several constructions that come from different sections throughout the entire semester here. The first couple come from chapter 1. There's one of them from section 2-1, a couple in chapter 5, and so on. So rather than teach them as a broken, segmented topic like that throughout the semester, we gather all of them together and create one lesson called Extra One, EX1, as you can see in the title. And it's going to be all the constructions that you would have seen from these first 6 chapters of the course. You're going to see another one of these at the end of the second semester before we jump into end of course exam review, literally titled EX2, all the constructions from the second semester. Now, what is a construction? So in very, very simple terms, as you can see in the box at the top, a construction goes all the way back to the beginnings of geometry, basically the building blocks and the foundations a few thousand years ago. How do we construct and prove concepts without the ability to actually measure? Because ruler and protractor and things like that are more modern inventions. The ability to actually measure a specific length and tie a number to it, those are concepts that have come about in the last 1,000 years. All the way back when ancient Greeks started geometry, the only thing they had was the ability to draw a straight line and the ability to draw an arc using a compass. So how do we actually build congruent segments, perpendicular lines, things of that nature without the physical ability to measure? So we're going to take a look at 7 of them for this particular section. We'll get into how each of them works as we go through them here. The first couple are how do we construct congruent items? So how do we create a copy of a segment and how do we create a copy of an angle? So suppose we have some random segment. So let's draw this one from here to here, and we want to create a copy of it somewhere. Well, since I don't have measurement tools, I can't just simply measure the length and then draw another one somewhere else. I have to be a little more creative with how we do this. So we're going to follow the steps that are listed here. We'll take the first endpoint, and this is going to be the start of my new segment. I need to use my compass, which I can take the compass and I want to open it to the length of this segment. And notice what it does. It creates a circle around the length of that segment. If I move my dot on either endpoint, notice the circle passes through the other one. I have created one complete circle, one complete arc that measures the length of this original segment. So if I come down here to my new point and place this, any dot on this green circle is now going to work. So we'll just take a segment and draw it, let's say, at random here. These 2 segments have to be the same length now. And luckily, a couple thousand years of technological advancement and whatnot, we can go measure them just to prove it. This comes out to be 4.03, and this one will definitely be the same. And we can test multiple examples because we can change the segment. They stay the same number, they still stay the same number, and they stay the same number every time as I move them the whole way around. We are guaranteed those 2 segments are congruent because I used my compass length, however long the original one was, to create the radius of this circle. So any dot is guaranteed to be the same length away. The second one that we've got here is how do we create a copy of an angle? So we need to generate congruent angles as well. So let's draw one random angle here. And notice we don't have a measurement, so same idea. I'm not going to measure till the end so that we can actually prove that we've done it correctly. For right now, no measurement, it's just some angle. Step number 1, as you read them here, we want to draw the first ray. So we want to draw a ray going out this way. That is going to be the start of an angle. Basically, it's going to be this side, because remember, the length of the ray or the segment is irrelevant. We just need to make sure they're the same space apart to generate the angle measurement. So we have some bottom line here. Now I need to figure out, where does my second one go? Does it come out here? Does it come out here? Does it go here? I have to be exact. So we're going to use the same compass concept. I want to just put a point about here so that I can use my compass to generate an arc of this length. So let's go through, take compass, I want to draw one. And if I put it here, notice it goes through the vertex of the angle. If I put it here, it goes through the extra dot we created. I want to put one there. And then according to the step, I want to do the same size arc down on my other one too. So this is the step that's here. Draw the same arc on your vertex and the endpoint array. I've created the same green circle based off of this length on both pictures. Now I need to know how far apart they are. So same idea. If I draw a segment going across to here, I can do the same compass trick. My compass will be the size of this. Notice it hits both sides of the angle. So I'm going to do the same thing here. If it's on one of them, where it crosses my other circle, this has to be where my second ray goes. So we'll draw a second ray through that intersection point. We are now guaranteed that these two angles are the same measurement. Now let's hide a little bit of our work so that we can actually see it easier. While the construction is built correctly, we don't want to have all this mess here, so we can hide them. It's a little easier to see. These two angles are going to be the same. To prove it, we're just going to actually go measure them. So that one came out to be 51, and that one came out to be 51. And if we start moving the ray around, notice they go in movement together. So they'll be the same measurement every single time. It's an absolute guarantee that they are congruent angles to each other. The next few constructions that we have are how do we generate different types of lines. So now that we've gone through and created copies of things, now how do we start splitting things in half? So we're going to take a look at perpendicular bisector, angle bisector, things of that nature. Let's generate some lines. The perpendicular bisector is really easy. If I've got some random segment out here and I want to create a perpendicular bisector for it, all I have to do is draw the same arc off of both points of the segment, and the perpendicular bisector is where they drop through. That's a property directly from back in chapter 5. Any point that's equidistant from the endpoints has to be on the perpendicular bisector. So we do this the real easy way. I want to create this and draw it off of this point. And I also want to create it and draw it off of this point. Where the two circles intersect has to be the perpendicular bisector. So now if you just look at that picture, it looks legitimate. But again, modern advancements, let's go actually measure it and physically prove it. So the idea is from here to here should be the same distance as from here to here. And this should be a right angle. Well, let's physically prove it. If we pick the left side and measure its length, it's 2.05 units. And the right side, also 2.05 units. So we are good. The length is the same. And then the angle had better be a perfect right angle for perpendicular, which sure enough, it's a 90. And if I start dragging points around, I'm going to end up finding that same thing stays constant. Still the same measurement, still 90, still the same measurement, still 90. I can do this anywhere in the picture. They'll stay the same measurement and stay 90. This is the perpendicular bisector for that segment. We have a very similar method when we go to do angle bisector. We want to try the same idea. We want to find a perfect center line. So let's draw some random angle here, and I want to split it in half, put one line through here. Well, we're going to do the same logic. I'm going to use my compass tool to go through and create an arc, as it says, centered on the vertex, as long as it passes through both sides of the angle. So we could use the compass, we could draw the circle, it'll do the same thing. I just care that it hits both sides of the angle. The idea is I now want to do the same thing I just did with perpendicular bisector for this distance, the size of this angle, the space across from it, because that will give me dead center middle and I can draw a line out through it and split the angle in half. So let's draw the segment that connects the two spots across, and I want to do the perpendicular bisector idea on this segment. So we'll take our compass. I want this length off of its one endpoint, and then I want this length off of its other endpoint. Where they cross, must be the bisector I want to draw. So we'll go through and we'll just draw a ray, starting here at the vertex and passing out through where those circles intersected. Now, just like we did with one of the other ones, let's hide a lot of our extra work here because we don't want a lot of clutter. So let's go hide all of those so we can see them. The real question is, have we done this correctly? Is this an actual true bisector? Well, let's measure it and find out. From here, the top portion's 32, while the bottom portion is also 32, so it looks like it's good so far. And if we start moving the angle around, notice they stay constant. That line is the angle bisector. It has split it in perfect half every single time. It's 100% perfect. The last line that we construct is how do we build parallels through some point. So we'll read, we have a parallel line through a specific point, excuse me. So here's a random segment, and let's just put some point up here, for example. I want to generate a parallel line that passes through this dot at the top. So following the steps here in the list, we want to draw any line at any angle through that point. It doesn't matter. So we just want to start here, and I want to make sure it passes through this line. Doesn't matter if it's on an endpoint, doesn't matter anywhere on this. I just want to put a line straight down through it, because now here's what we're going to do. We're going to create one of the properties that you have from back in chapter 2. We are going to create a copy of this angle up here at this point, because then we'll have a pair of corresponding angles that are congruent, and as a result, the lines will be forced to be parallel. So let's do the angle construction. So if you need to, you can always go back in the video how we created a copy, but we'll go through, we'll generate the same circle. So I want to create a measurement, say to here, and use my compass. So we'll take this measurement on the vertex, and we'll take this same measurement up on this one. I've created the same exact arc on both ones, from here to here, and from here to wherever my line's going to sit, somewhere around here. Now it's going to be the same idea. I need to do the measurement across from it so that I can go do that up top. So let's create a segment going across so that I can use my compass to figure out its size. I notice it hits both parts, no matter which one I am on this one. So if I do it up here, it tells me exactly where my second line's got to go. It's got to pass through this point right here where these cross. So we'll draw our second line through that spot. Now, if we've done this correctly, these should be the same angle measurement, and as a result, these two lines have to be parallel. So let's measure the angle first, an 86-degree angle and an 86-degree angle. Now the line should remain parallel if we start moving things around, which notice they're still parallel. If I start moving this, they're still parallel, nothing's changed. And if I start changing the angle, they're still parallel. They move together in unison. And if you want real proof that they're parallel, if you go all the way till it's 180, they're literally the same line sitting on top of each other. So you know they are never actually touching unless they become the same line. So they are constantly parallel the whole way through as they move. We only have 2 more constructions, and the last 2 come out of chapter 5. How do we construct a circumscribed circle, and how do we construct an inscribed circle? And if you remember back in chapter 5, that's the idea of 2 of the points of concurrency that you learned. How do you generate the circumcenter, and how do you generate the incenter? So we need to start with a triangle. So let's say we've got this triangle here, and we want to do a circumscribed circle around the outside of it. So if we go through, we need to generate the perpendicular bisectors for 2 of the sides. So we're just going to do one at a time. The perpendicular bisector argument, if you need to go back and look earlier in the video, is basically draw the same arc or the same circle that's the size of your side. So we'll draw these 2 and construct the perpendicular bisector based on where they crossed. Now, because this picture will get very cluttered because we're doing it multiple times, I am absolutely going to hide all of the extra work because we don't need any of the extra information. We just need the fact that line splits this side of the triangle in half and is perfectly perpendicular. The measurements are left to you if you want to try and measure them out on the screen. We're going to do the same exact thing for one of the other sides of the triangle. So we'll go from here to here for this side and back. And I'm going to draw the perpendicular bisector where those intersect. And the same idea, I want to hide all of the work we did for this construction because I don't want it to be super, super cluttered here. There's two of them. Now, technically, if you want to draw the third one, I mean, logically, it would be right about here because that's halfway across the segment, and perpendicular would be straight up, which notice it lands right here on this point. This is your circumcenter from back in chapter 5, which means it must be the center of a circle that hits all 3 points of the triangle. So all we have to do is the last step that's listed here in the construction, use your compass on this circumcenter and connect it to any of the points on the triangle. And notice the green circle hits all of them. So you've generated your circumscribed circle. It hits all the points of the triangle. And if you start moving points around, everything else moves to compensate for you. So it always remains the 3 points of the circle are on the 3 points of the triangle as well. And you could spin it around and all the rest of it. Also from chapter 5, we want to do the same exact thing, but we want to do the inscribed one. We want to make sure the circle stays inside the triangle. So same idea. We'll start with a random triangle here. And now we want to generate the incenter to create an inscribed circle. So we know from chapter 5, we've got to go do the angle bisectors. So we want to do the same logic that we did before, but we want to do it for the angles, not for the sides. So we'll create one arc / circle here. And then I want to split this angle in half. So we'll go across to where it hits here, and we'll come right back across here. Where those two circles cross must be the angle bisector. So let's draw it right through there. And again, just like the last one, since we're going to do this multiple times in this picture, I want to hide all the extra things that we did because this is going to get very, very cluttered very fast. I'm only interested in this one single line. I have split this lower left angle in half. So let's do it for the lower right one as well. If I take my compass and circle tool and move this out to here, now I need to split the angle. So we'll go across the angle to there and back across to there. Where those two circles intersect must be my angle bisector. So we'll draw in that line. And again, let's go hide all the things we just did because we don't want to keep this cluttered. We're only interested in that line in the first place. So the construction, if you want to actually build your bisector, go back in the video and watch that specific construction. For our purposes here, we're just actually using it. All of that hidden away. These two, if you want to draw the third one, but you can start using just your imagination, just as an estimate of, are we doing this correctly? If I split this angle in half, it would be a line that goes right about here-ish. And sure enough, it's going to cross this point. You know all three of them have to cross at the incenter, but we only need two so that we know where the point is. Our incenter is right here in the middle of our triangle here. Now to create the actual inscribed circle, I need to draw a perfect perpendicular line to any side of the triangle. So I actually have a tiny bit more construction to do. I have to take from here and I have to do a perpendicular going straight down to this side. So we're going to just draw out to here. That way I've got 2 points where it crosses this bottom side. And now let's do the perpendicular part for this segment. So if we go across to here and back, I can draw a perpendicular right down through to where the circles cross. And again, like we've done in every step so far, let's hide all the things we don't need, because again, cluttered picture makes it tough to see what we're actually doing. So let's hide those things. This right here, from here to the edge of the triangle, is going to be the radius of my circle. So let's go ahead and just draw a circle centered on the incenter and connected to where these two cross. And notice the green circle hits each edge of the triangle and stays perfectly inscribed within it. And if I start moving points around, the circle moves with me, changes size, guarantees that it's always inscribed perfectly as we start moving around. It is the inscribed circle. It'll never go outside of the triangle in any way, shape, or form. That's everything for constructions. The only thing to close on in this video is the problem types that you'll see. While it's great to actually be able to physically use the tools to construct them and whatnot, the reality is on the semester exam and on the state's end of course exam, the only thing they ever ask you of these construction steps is the actual steps themselves. They tend to be multiple choice questions and very rarely fill in the blank problems, but they'll only ever ask you, here's a picture that's partially done. What's the next step that should be taken, or what mistake has been made because they were trying to build this? Those are the kind of questions they get at that will ask you, and you'll see. You're not going to be asked tons of problems on, here's a blank picture, can you do it? They're not going to hand you a ruler and a compass and whatnot and turn you loose on a computer-based test or on a multiple choice test like the county's semester exam. You're going to see the same style questions in the problem set for this section. All they're going to be are, here's a picture, and you're going to be tasked with, what are they trying to build? If they're building this construction, what's the next step? If they're building this construction, what have they done wrong in this picture, and so on. So definitely study how the steps work and get a good idea in your mind of what the picture looks like as each component of it is built. But don't be overly worried about having to actually grab a physical tool and trying to draw it yourself. They're not going to ask you that for this concept. That's everything for the first semester's constructions. If any questions come up, make sure to ask your teacher, and see you guys in the next chapter for semester exam review.